I'm engaged in computer security since 2002, and I started, actually I was a member of one of the first reverse engineering groups back in Greece. And my first years in my career, I spent them by working as a network security engineer, then I jumped to developing. And the last about 5 years, I focus on Android security and especially malware. Now, about a year ago, I joined Microsoft's Defender research team as a senior security researcher. And the reason that I'm here is to show you how an Android application can drain your wallet from the sense that one Android application, how an Android application can actually have a financial impact on the end user. And before we start this presentation, let me go through the outline. So first of all, we're going to see what is a premium subscription, how this is performed, and how it can be used in order to enable the users to purchase services, products online, and get charged in their phone bill. Next, we're going to see how a malware, how an Android app can perform such a subscription in, let's say, a deceptive way without the user being aware of it. Then we're going to see how this malware, how this type of malware manages to evade detection and being one of the most, let's say, prevalent malware categories in the Google Play Store. Then the other thing is how it gets published in the first place on the Google Play Store, how the developers, how the malware developers manage to publish the software in the Google Play Store in the first place. Then we're going to talk about some rough ideas on how we can detect this type of malware. And finally, again, some rough ideas on how actually we can prevent this type of malware from even being published in Google Play Store. Now, before I start explaining how this malware works, let me go through some definitions that we are going to use in the next few slides. And the first thing that I want to talk to you about and I want to define is what is billing fraud. So by billing fraud, we refer to the malware category, which contains code that charges the user in an intentionally deceptive way. And we have a couple of subcategories of billing fraud. We have call fraud, we have SMS fraud, and we have toll fraud, with the last one being the most interesting one, and the one that we are going to focus in this presentation. Now, when it comes to toll fraud, when it comes to this type of malware, we're talking about a malware family with a multi-billion-dollar yearly revenue, and one of the most prevalent malware categories according to the Google's Play Store Transparency Report. It is also very popular. I'm sure that many of you have heard about the Joker family. Some of you have heard also about the Bread family. And this is, although actually there's not a lot of posts out there on how this malware works. And it is such a popular, let's say, malware due to the fact that it uses the Google Play Store as its main distribution mean. Now, the next thing that I want to talk about is what is the WAP billing mechanism. It's something that we're going to use in the next slides. So let me define what is a WAP billing mechanism. So by this, we refer to the billing mechanism which uses the wireless application protocol in order to allow the user to purchase products, services online and get charged in their phone bill. Here again on the right side, I have an example of such a subscription flow, so how someone can subscribe to such a service. So first of all, only customers can subscribe to be eligible for subscriber benefits. And who are the customers here? We're talking about people who are, let's say, registered to a specific SIM operator. So these users who are registered to a specific SIM operators may subscribe by using the respective WAP-enabled website or the Android app, as it points out in the 4.243. And the customer will receive an SMS which will inform about the billing price, the rate, the billing interval, and the next billing date. And please note on the last one, which says that the customer cannot subscribe to one subscription service more than one time. We're going to see how actually the malware tries to track that and how it's going to bypass that in the next slides again. So let me summarize what actions a user should take in order to subscribe to a service. So as I said before, first of all, it has to navigate to a specific website. by the time that the server is going to receive this request, it's going to send back what we call a landing page. This landing page contains a subscription button on which the user has to click on it. And when the server receives the new request, it's going to send back what we call a PIN, an OTP, a PIN. This is sent usually using an SMS. So by the time that the user is going to receive this SMS, it has to send it back to the server is going to verify it, and finally send back the SMS that I talked before, which inform the user about the billing rate and all these kind of things. And the other thing that please notice that the steps 4 up to 6 are not always there. This flow actually depends on each SIM operator. Someone may use this one, or someone may be a little bit different, but it's all about the same. It's all about this one here. Now, what is a fraudulent subscription? So a fraudulent subscription is a subscription which takes place without user interaction. The user won't interact with the software, without user consent, and actually without even being noticeable to the user. So the user won't understand a thing about it. So the malware has to take these steps that the user did before in order to achieve this type of subscription. So first of all, it has to disable the Wi-Fi connection or wait for the device to switch to a mobile network. That's the first step. Then navigate to the subscription page. How? Then simulate the user click on the subscription button. Intercept the PIN which is sent from the server to the user. Send this OTP back to the server. And finally, keep the process silent in order for the user not to understand and not actually the process to be noticeable to the user. So one very important step before performing these actions is to identify the SIM operator of the device, the SIM operator actually on which the device operates. And this is due to the fact that each payload, each app, targets specific SIM operators. And as I said before, each SIM operator has a specific flow, so the malware has to take specific steps. And this is due to the fact that they target specific SIM operators. This is why actually they target these specific SIM operators. So this type of information can be retrieved from your device by using the MNC and MCC codes. And for example, an Android app can simply call the getSIMOperator method or the get method of the system properties class and get these codes. The only difference between these two calls is actually that the first one can simply be invoked by importing the telephony manager class, while the second one, for those who are familiar with Java, it has to be called using reflection. Now, on the lower side, I have one example of one of the latest Joker payloads, which does exactly that, what I said right now. So it will check if the SIM operator starts with 655, and then it will start the steps that we're going to see in the next slides. And at this point, 655 actually is a SIM operator, which corresponds to a South Africa SIM operator. All right. Now, the first step, make sure that the device operates on a mobile network. So how we do that? So either wait for the device to switch, or either force the device to switch. Wait for the device. So get a network info object, observe this object, and try to get the type of the network. If the type of the network is mobile, then start to do the next steps. Now, the other way is to disable the Wi-Fi of the device. And this, before SDK 29, was done by using the set Wi-Fi enable of the Wi-Fi manager class. And after SDK 28, we saw something different. Actually, this one was deprecated in 29, so we saw something different, which actually was, I could say, better for the malware developers. So what we saw is that they were creating a request builder, a network request builder object, so define some specific capabilities in this builder, then request this network from the connectivity manager, and finally, when this network was, let's say, ready, bind the process to the network. And again, here on the right side, I have an example of how this flow goes. On the upper side, I have the actual code, while on the lower one, I have a demo code, which is easier to read. You don't have obfuscation, it's not obfuscated. So create a network request builder object, define some capabilities there. We want the device to be able to connect to the internet, and we want to use a mobile network. Then request this network, use the connectivity manager, and then finally, when the network is available, just bind the process to the network and use the network. Now, just note here that the device can also have the Wi-Fi enabled, and this app can just bind to the mobile network. So it's even better for the, actually this update was even better for the malware developers due to the fact that they don't have even to disable the Wi-Fi. Anyway, the next step is to get offers, to get the websites where the malware is supposed to navigate in order to do this type of actions. So it will communicate with the command and control server. The communication is usually customized. What I mean it's either encoded, or they use some kind of customized encoding or encryption, or zipped or something. So they will retrieve, usually they retrieve some kind of a JSON object which contains something similar to what you see here. So something important here is the offer URLs. So it will get one of these offer URLs, which will lead to a redirection chain, as you see here. And this redirection chain will finally lead to the landing page. Now, this landing page will be loaded to a web view which is not visible to the user. So the user, again, so far, won't understand something. Now, another, let's say, an important Android operating system component which is used from this type of malware is an Android OS handler. And what this handler is doing is actually observing the subscription process, the cycle, and acting according to the phase that the subscription process is currently in. So when, let's say, the page was loaded into the web view, the malware will send a message to this handler, or when SMS has been received, the malware will send a message to this handler, and according to the ID, according to the what parameter of this message, is going to perform some type of an action. So here I have, again, an actual code, which, as you see, gets the message, checks the what parameter, and acts accordingly, according to the phase. So one very important phase is when the page is loaded. We are here now. I mean, we have loaded the landing page on the web view. So how now the malware is supposed to simulate the click on the subscription button? So we saw a couple of ways of doing that, using, for example, JavaScript interface or something. But a very common way of doing that is by injecting JavaScript code. And JavaScript code similar to the one that you see right here. So what this code is doing is actually scrapping the page and searching for elements which can be clicked or submitted. Then it will filter those elements. Let me go through the, yeah. So it will filter those elements, searching for ones that they are, let's say, relevant to the subscription process. So search for tags like confirm, yes, click, things which, like I said, are relevant to the subscription process. Then it will send all these elements to the function C, which you see here. And what this function does is actually acting in two steps. So the first step is to call the JDH function. Now, this JDH function will check for a specific cookie. So if this cookie has been set already, then it will return false. If this cookie has not been set, it will return true and will set the cookie. Now, what this cookie does is actually marking the page in order for the malware to understand that this page has been visited in the past. So we subscribe the user already to the service. We don't have to subscribe the user again. We can subscribe the user again. So this cookie does exactly that, just marking the page which the malware already subscribes the user. So it will send back to the function C that I explained to you before, true or false, and depending on this parameter, the function will just click or submit the specific element. Now, okay, now we are at the point that the malware, let's say, simulate the click on the subscription button. Now the next step is to intercept the pin which is sent from the server to the user. And we saw a couple of ways of doing that. So one way is using an SMS broadcast receiver. Another way is binding the notification listener service. Another way is using the SMS content observer. And let's see how this thing works. So in short, the app has to declare some specific permissions, and it needs these permissions in order, some of these permissions actually, in order to define a broadcast receiver, which broadcast receiver, in the on-receive callback, it will just get the message, the incoming SMS, examine the body of a message, and search for specific keywords, which, let's say, are corresponding to the specific SIM operator, to the specific service provider. So it will extract the PIN and use an API called the send text message, for example, in order to send this message back to the server. Another way, which actually is the most common one, and it has the same logic, although it's a little bit different when it comes to implementation, is bind the notification listener service. So extend the notification listener service, create a class, and when notification, you know, these notifications that they are posted in your device, when this notification is posted, check the body of the notification, and if, again, it has something, let's say, relevant to the subscription process, extract the PIN and send it back to the, I missed the steps, so send it back to the server. The last one is using Content Observer. So what a Content Observer does is receiving callbacks when changes to a specific content happen. And what we care more here is about the SMS content. So when the device receives an SMS, this content is going to change. So the specific callback there, the on change, is going to be triggered. And again, the same process is going to filter out the body of the message and send the text to the server. Final step of this long process is to keep everything silent, right? And in order to do that, and since SDK 18, every app which extends the notification listener service is authorized to suppress notifications from other apps. I don't know why. Anyway, and there are a couple of API calls in order to do that, using the cancel all notifications, or cancel specific one, or cancel an array of them. Another way of doing that, although it's a little bit more tricky due to the fact that the app has to be the default SMS app, is to abort the broadcast when an SMS has been received. So they extend the broadcast receiver, the SMS has been received, and they just abort the broadcast in order to dismiss this notification. Okay, so just to summarize the process, because we said we talked about a lot of steps. So what we talked so far? The WAP billing mechanism. So what is a WAP billing mechanism? It is a mechanism which can be used in order to let you purchase services, products online, and don't have to pay directly. You can just get charged in your phone bill. This process requires from the user to take some specific steps, right? Then this type of malware simulates these steps, and these steps include to navigate to the website, simulate the user clicks, intercept the PIN and submit it back to the service provider, and suppress all the notifications in order to keep the process silent from the user. All right, cool. So we're talking about a very long process. We're talking about a lot of API calls. We're talking about a lot of permissions. So it can't be that hard. Many of you might wonder right now that it can't be that hard to detect this type of malware, how it can be so prevalent in the Google Play Store since actually 2017. So the answer here is actually that this malware is very difficult to detect. And it's very difficult to detect because it uses steganography. It will use steganography. The payloads are hidden in seemingly banning files, for example, PNG files, JPEG files, in the assets folder, or, I mean, the APK is huge, so you can just hide it anywhere. Cryptography, with keys, different keys from one sample to the other. So even, let's say you create a signature which, let's say, detects some of these samples, or let's say one specific version of the samples, then even each sample can have a different key, and you can't just miss one sample to another. The other thing, of course, is obfuscation in order to evade static type signatures, and dynamic code loading. What I mean by dynamic code loading, the code which does the steps, is doing the steps that you saw before, is not actually there. It's going to be downloaded from the web, it's going to be loaded, and it's going to be executed. And finally, clocking. What is clocking? Clocking We refer actually to the set of actions which the malware performs in order to detect if it's running in some kind of a VM or some specific condition doesn't apply. For example, it's not published in Google Play. Or there are actually funny things that we saw on how this malware tries to evade, actually to detect if it's running in a VM or something. So let's see a specific case of one of the, which actually let's say, concentrates all these things that we talked so far. So actually, we're talking about the Messenger app. Many of you have already installed this app in your device. It had quite a lot of installs, and was actually published in the Google Play Store before a few months. So the first thing that this app is doing is simply check if it was published, if it's still published in the Google Play Store. So we will just send a request to the Play Store and see if the specific package is still published. So if it's still published, then it will go to this process here. So this process here is doing the following. So we are entering the stage 1. So what is going on here? The malware will check the assets folder and try to find an asset which ends with 355, right? Now, please note that the first versions of this APK didn't have this asset there. So it was unweaponized. It was actually, this specific asset was added in the later versions. So it will check for a specific asset. It will get this asset. And then, on the next step, it will decrypt this asset, actually using a key, which was found to be hard-coded in the specific DEX file. So it will decrypt this file using AS, and it will drop another file, which is actually an ELF file in the data folder of the app. This is an ELF file. It will be loaded using the system.load function, and then it will call a native function which is implemented in the native layer. So we are now on the native side. And when this ELF gets, let's say, decrypted and dropped in the data directory, you won't see much there if you try to decompile it. All the strings were XORed. So we have to go through each one of them in order to decrypt it because they have different keys for each one. And for example, this one has a key which was a GIF. Another one has a different something. So by decrypting these strings, XOR them back, we found calls to the DEX class loader. And actually, we found calls to another class which wasn't anywhere, in the initial APK. So it was proved that when everything was there, where all these, let's say, strings are decrypted, everything is on set, the malware will check for another asset file. So this asset file actually is this one here, which ends this time with 300. And this asset file turns to be decrypted and turned to DEX file. So it will decrypt this file, it will XOR this file with a key, which is sent from the Java side. So this file will be decrypted, will be dropped to the data folder, and then again it will be loaded using the DEX class loader, and the load class, which this time will load the class that I said before. Now this class, the com.addsView, is actually the DEX file, which was just right now, let's say, decrypted. Finally, we'll perform a JNI call static void method using this specific call in order to call a function from this class, this specific class. And here we are in the DEX file now. So here we found the command and control server, which was hard-coded there. And what this actually DEX will do, it's not much besides communicating with the command and control server and download another file. So this file now is a jar file. And this jar file is going to be, again, loaded using the DEX class loader. And when executed, it's going to perform the last step, which is to check the SIM operator. If the SIM operator is starting with 655, then it's going to start the process, the cycle that I talked to you about in the first few slides. So let's summarize this also because it's quite long. As I said, we have an APK, we have an SMS app. The first thing that it's going to do is just check if it's published, get a file from the assets, decrypt this file, and drop it as an ELF file. The ELF file will get another file, which is a DEX file, decrypt it, And then this DEX file is going to communicate with a command to control server, download the jar file, and finally the jar file will check if the SIM operator is targeted, start with 655, and start to do the cycle that I talked to you about before. So now you have an idea why we can't detect this type of malware, right? Why it's so hard to detect it. So another thing, now that we have a nice overview of how it evades detection, how it does this, let's say, toll-for process, how it does this fraudulent subscription, is how malware developers manage to get this malware published in the Google Play Store in the first place, how they do that, and how, I mean, Google, let's say, allows that in the first place. So there is a strategy used from malware developers. And this strategy includes specific steps. For example, use open source apps, which are very easy. I mean, they are very popular. They're very easy to install. They're very easy to get a lot of installs very quick, get popular very quick. That's the ultimate target. So these apps are wallpapers, lock screens, beauty editors, cameras, communication apps, messaging apps. So they will upload clean versions of these apps. The first few versions are going to be clean, not weaponized. And they have, let's say, specific thresholds. Let's say if the app reach a specific number of installs, then they're going to update the app and add, let's say, weaponize the app and add actually the payloads that I talked to you about before. Another thing is try to stay as much as, they're going to be detected at some point, but just try to make this time as long as you can. So they're going to separate the malicious flow from the initial APK as much as they can. So as I said before, they're going to download the DEX file and load it and execute it instead of have the DEX file, this DEX file, the malicious DEX file, in the APK from the start. Now, thankfully, this, let's say, penetration strategy, which the malware developers are using, creates what we call secondary signals. And these secondary signals include the following. For example, we have an excessive set of permissions, which actually, I wouldn't say excessive, but I would say more not up to the application's functionality. For example, you have an app which is a wallpaper app, and this wallpaper app requests you to bind the notification listener. What a wallpaper app will do with the notification listener, it doesn't make sense. So another thing is they might request SMS permission. So what they're requesting, it doesn't, let's say, it's not on page with the functionality of the app. Another thing is that they have a lot of common user characteristics, interface characteristics, for example, icons, policy pages, buttons. All these things seem to be quite common between these apps. Another thing is similar package names, suspicious developer profiles. You're going to see developer profiles that they are very common between them. They're just a page with a name, which name seems to come from some kind of an automated process. So it's, let's say, easy to understand from this type of, at least to get suspicious from this type of signals, right? Not 100% to say that this is actually malware. And finally, we have the user complaints. Although here sometimes you shouldn't rely on the user complaints, especially if these complaints are, not complaints, actually I would say comments. If these comments are, let's say, all right, what a great app or something like that, you shouldn't rely on this type of, comments due to the fact that we saw cases that the malware itself tries to post comments on the page which is posted. All right. Okay, now we have, I guess, a good overview of how this malware works, how it gets published, how it evades detection, and how actually performs the steps that I told you about in order to do this, let's say, subscription. Now, let's see some rough ideas on how we can detect, what options do we have in order to detect this type of malware. And let's start from the client side, right? You have your AV in your device, what this AV can do in order to detect this type of malware. And the truth is that we can't do much at the client side. So the Android operating system imposes serious restrictions on what one application can get for another app. It's very difficult, let's say, to get some info for another app. Each application is trapped in its own sandbox, and the info that one app can retrieve for another app is, let's say, controlled from the system. So you don't have many chances at that point. A thing that you can do, of course, is, let's say, do some kind of static scan, which, again, some help from the cloud, or maybe observe the HTTP communication in order to see some kind of, let's say, suspicious communication with the command and control server. And, of course, maintain some type of blacklist of command and control servers. If you see such a communication, then just alert the user, or in order to alert some kind of suspicion. Now, on the cloud side, though, we have a lot of options, although they don't seem to be so far, like I said, very, they have a nice result. But the pipeline that you are going to see here is actually a pipeline which we try in order to achieve the best result using the less amount of resources. So we start with a steady feed. We have a feed of APKs. This feed might be something like researchers which, let's say, feed our system with APKs, or even the Play Store itself, or a device. I mean, we can just, the user can submit an APK from the device. So you have a feed. And the first step of this pipeline, the first step is to filter the apps for secondary signals, secondary characteristics, the ones that I talked to you about before. For example, if the app has similarities with other, let's say, toll fraud, secondary signal, again, developer's profile, number of installs. And the result at this point is going to be either the app is going to go on the next stage, or the app is going to be suspicious, simply suspicious, is going to be rescanned, or finally is going to just skip due to the fact that we can't, let's say, we didn't reach a specific threshold of this type of characteristics. So the next step is to start to scan the app for specific, let's say, to perform a static scan. So scan for specific API calls, or specific strings, or specific permissions. And again, the result is going to be the same, but we're not going to be sure due to the fact that, as I told you before, we have this evasion detection mechanism. So either it's going to be suspicious, or either it's going to be skipped due to the fact that it's missing some, let's say, important permissions, or it will go to the next stage. Which next stage is the most, let's say, demanding when it has to do with resources, because we have to, first of all, interact with the app with, let's say, a clever way. We have to clever interact with the app, and how you do that, right? I mean, it's, we try to, let's say, cause as much functionality as we can by interacting with the app. And this is actually a very difficult problem, because you might have some kind of logging wall, or something that the human has to interact in order for the app to proceed to the next steps. So actually, this is a big problem, how to do that. Let's say that you solve this problem now, then the other thing is to perform the dynamic analysis part, which is intercept the HTTP, HTTPS communication, perform some binary instrumentation, log the API calls, intercept the API calls. And what I mean intercept, so change the return values in order to trigger additional behavior, additional functionality. Then we have to dump the memory for DEX files, because many of these apps are using packers, or as I said before, they can just drop something and then load it in the memory, so you can just dump the memory in order to get these DEX files. Observe, of course, the data directory of the app in order to monitor for dropped files and see if the application is dropping something and just loads it. JNI trace, JNI calls, trace the JNI calls, and finally dump the memory on the native space, because we, especially recently, especially the last maybe year, we saw a lot of malware developers moving on the native side. All right, so what is the final result of this, let's say, process, of this pipeline? Not much. Again, we have to create signatures, right? We have to create signatures, we have to enrich our database, and actually, what we want is to be able to catch this, to detect these samples before, let's say, reach to the final point. So detect them in much earlier stages. All right, And reaching now to, let's say, the end of this presentation, I want to talk about how we can prevent this type of apps of being published in the Google Play Store in the first place. So, starting from November 3rd, 2021, Google took an initiative in regards to the permissions that can be allowed to a specific app. For example, an app which, let's say, requests some permissions that they are going to retrieve some personal information or SMS permissions or these kinds of stuff have to be, let's say, justified. So the developer has to complete a permission declaration form in order to justify how I'm using this type of permission, what I'm doing with this type of permissions. What we didn't see so far, and this is the, let's say, the unfortunate of this action that Google took, is the notification listener, right? So, as I said before, the majority of this malware actually uses the notification listener, abuses the notification listener in order to do this type of actions. So, we still see apps, for example, wallpapers, or this type of apps that I talked to you about before, the most abused ones, to still be able to use this type of service in order to do the steps that I talked to you about before. And with this, I mean, that was, let's say, a wrap-up of all these things. If you have any questions, please feel free to ask. Thank you.
Okay, so thank you, Dimitrios.
Thank you very much.
Any questions? Okay, one here.
Hello there.
Hello.
When you're doing the analysis for the Android malware, do you use an emulator or real devices? And what's the advantages?
Yeah. We can't, let's say, afford, we can't afford. It's something that you can't have many real devices. So you have to end up with some kind of an emulator at the end. So you have to use an emulator, yeah. Usually that's the common case, except if you have some kind of a special case which can be, let's say, forced to a different pipeline in order to pass through a real device. But the common case is an emulator.
Okay, thank you.
Another one here.
First. Thank you. So for me, it's pretty clear why you can't detect using static analysis these types of applications, but it seems like an easy job to detect them using telemetry. So in runtime, of course, why do you think Google doesn't make an effort to detect these types of exploitations in runtime using their own telemetry? Because these API calls seem to be really specific and only for these types of purposes when used in a group.
All right. So imagine you are Google, right? I mean, you have your Play Store, you have the app installed on the device. What type of information you can retrieve for one app? I mean, you don't have, like I said before, you still have restrictions when it comes to. I mean, even Google, despite the fact that it is Google and it's the one that actually, let's say, develops the specific frameworks, all the frameworks, and let's say it can interfere in this process. It is very hard for them to be able, let's say, to detect this due to the fact that they have also restrictions that they have to follow the restrictions that they apply by themselves, right? So they can't, let's say, break the sandbox. They can't break these kind of things. They can't be that intrusive. I mean, that satisfies your question.
Yeah, makes sense.
Yeah.
Thank you.
Hi. I was very surprised to see that the notification permission is not included in that Google agreement. So couldn't this be used to steal one-time passwords like Steam and...
Yeah, just make sure when an app requests for notification listener, to access your notifications, just make sure that you trust this app.
Yeah.
It's one of the most, it can be used actually to get a lot of info out of the device. It depends actually on what is pushed in the specific notification, what the app actually is getting from this notification. So if there is a pin there, whatever there is there, it can be retrieved from the app which extends the notification listener service. So yeah.
Literally anything like emails.
Whatever. That's a good point actually, and this is what this is on the developer side, where the developer, let's say, exposes on the specific service, right? So if you as a developer expose the email there, or you expose a pin there, or you expose some kind of a financial transaction, then yeah, it's something which is going to be retrieved from this type of software, yeah.
Spooky stuff.
Actually, this notification listener service is used from spyware also. It's very important to trust the apps that you approve this type of service. Yeah.
Thank you very much.
Yeah. Thank you.
Any more questions? I guess not. So again, thank you, Dimitrios, and
Thank you very much.
now we have. No.